All right, everybody. So what we're going to be looking at today is integrating inverse trig. This is actually not so bad. There's a topic later on that we're going to do called trig substitution, and people have a little bit more trouble with that than with this. This is kind of like a precursor. So it should be a nice short lecture because there's very little new material here. So let's go ahead and get started. So let's just say first that we learned derivatives for all six inverse trig functions. So there's like an inverse sine, inverse cosine, inverse tangent, inverse secant, inverse cosecant, inverse cotangent. And you learned the derivatives of all of them. However, you don't need all six of them when we're integrating, and I'll explain why. So consider this. You know that the derivative of sine inverse is 1 over the square root 1 minus x squared, because we learned that. And we know that a derivative formula is an integral formula, which means that the antiderivative of 1 over square root 1 minus x squared dx must be sine inverse x plus c, like that. But you also learned that the derivative of cosine inverse is negative 1 over square root 1 minus x squared, which would imply that the antiderivative of negative 1 over 1 minus x squared dx equals cosine inverse x plus c. But, all right, but do you really need that second one at all? And the answer is no. We don't need the second one. We don't need the second formula. Right? If ever you have an integral that has a negative in it, you would just do it like this. If you see, or if you have, an integral of negative, I don't know, I'm just going to change that, like negative 3 over square root 4 minus x squared, because we're going to learn how to do this kind, you would just take the minus out front, right? You can take minus 3 integral 1 over square root 4 minus x squared dx. And once the minus is out, you could use a sine inverse formula. So, cosine inverse? Question mark? No. Sine inverse. Okay? And that's kind of the idea here, is that we wouldn't need the three of them that are just the other three but with negatives. We don't need. So we're going to use sine but not cosine, tangent but not cotangent, and secant but not cosecant. Okay? And so we've already seen one of them. But we also need to see them for secant and tangent, like I just said. Okay? So the basic formulas, and these are not what you're going to remember, are as follows. So these are going to be your basic antiderivatives. Okay. So one of them you just saw. The antiderivative of 1 over square root 1 minus x squared dx is sine inverse plus c. The antiderivative of 1 over 1 plus x squared dx is going to be tangent inverse, if you remember. And the third one is going to be a secant, 1 over x square root x squared minus 1 dx. That is going to be your secant inverse x plus c. Okay? And so those are your basic antiderivatives. But we don't like these formulas because if we change the formula a little bit, like this one, this one, this one, into another number, then you have to do a substitution in order to work it out. And so what that substitution would look like would be something like this. So let's see, do I even want to do it? I guess it doesn't really matter. Let's do 1. Okay, so we're going to derive it, and then we're going to write down our real formulas. All right. So example, find. So this is not like an example like you're going to get in your book, but find the formula for this. Let's see here. The integral. I should have just said evaluate. So I'm going to go 1 over, and let's just go, the way they do it is they call this a squared. That's what the number is. This is going to be where a is a number, a real number, a positive real number, but you know, it doesn't really matter for this. Okay, so we want to find that integral. And so what we're going to do is, in order to make this work out, we are going to need to do the following. So if we take this, and we're going to factor out an a squared out of the denominator. And if you do that, you're going to get a squared over x squared there, dx. Now you can easily verify that. If that looks weird to you, then just distribute that a squared back in and just make sure that you agree that you do get that. Okay, so you factor out that a squared. Now that a squared is just a constant, so it can come out of the integral even. And then you're here. Now, in the denominator there, we have 1 plus x squared over a squared. But you could write that as 1 over x over a squared, dx, like that. That's fine. And now that's looking a little bit more like the formula that I wrote for the tangent up here. Right? Looking a little bit more like this. It's just that there's an x over a here that we're not supposed to have. So let's fix that with a U-substitution. So we're going to say let u equal x over a. Again, a is just a constant, which would mean du is dx over a, or dx is a du. So you make that substitution, we're going to get 1 over a squared integral 1. Your dx is a du. Your x over a is u. So you get that. So you take this a and this 1 over a, combine those, so you get 1 over a integral 1 over 1 plus u squared du. That is going to give you, well, that's the formula that we memorized. So you come back up here, we have memorized. That's the one that we saw briefly, right? So you come back over here, and now it matches this exactly, so we know it's a tangent inverse. Okay, so we know that this integral is a tangent inverse of u plus c. Okay, and then we put that, we replace the u back with what it is. So what is u? It was x over a plus c. And that's the formula that you're going to remember. Okay, so the formulas that you actually want to remember are these. Okay, so these are the ones you want to remember. The one that we just did, which was the integral of 1 over a squared plus x squared dx, is 1 over a tangent inverse x over a plus c. That's a good one. Then we're going to have one for the sine, 1 over square root 1, nope, not 1, right? We're changing that. A squared minus x squared dx. Now, just have to double check this here real quick. Hold on a second. For some reason, I always forget. Yeah, okay, that's right. So this, so it turns out that the sine inverse does not have a 1 over a out front, which makes it different than the other two. The reason for that is actually just, you know, if you redo the steps for sine inverse that we just did for the tangent, it just happens that when you get to this point here, where you've got like the 1 over a squared and then the a cancels out one of them, it turns out that there was only one to cancel, and so it goes away. Anyway, so back here. So this one's going to be 1 over a secant inverse x over a plus c. All right, and so these are the basic formulas that you're going to use. And so there's only two different types of problems that are on this homework, and both of them are going to use those three formulas for you. So what kind are you going to see? So let me pick a couple here. Yeah. Oh, that one looks complicated. Yeah, let's do a complicated one. Why not? All right. So here is an example. So we've got -5, 8t square root 64t squared. Oh man, this is getting rough. Minus 81 dt. Right? So here's what you should do. So the first thing you should do when you look at this is you should decide, well, which of the three is it, first of all. And just based on the form of it, right, you should see this t out here, and then that should remind you of that right there, okay, that x. So this looks like it's a secant inverse of some kind, right? So you think secant inverse of some kind. Secant inverse? Yeah, it is. Okay, so then what we want to do is we want to start turning this into the formula that we know. And so what is wrong with this, first of all? So the -5 shouldn't be there, but that's easy. We can take that out of the integral. The 8 shouldn't be there, but that's fine. We can take it out of the integral. And then there's a 64 here. Well, that shouldn't be here. We should take that out of the integral. Well, you can take it out of the integral, or you can do a U-substitution. So the way I'll do this is I'll say we should take the 5 and the 8 out first. So -5 over 8. Integral 1 over t square root 64 t squared minus 81 dt. All right, so there we go. We've already made an improvement. Now the only other thing we need to worry about really is that 64t squared. So what I'll do is I'm not going to take the 64 out. You might think that I was based on how I solved the previous problem that we solved, but I'm not. What I'm going to do is I'm going to rewrite that 64t squared as parentheses 8t squared, like that, minus 81. So all we did was we just rewrote that. Rewrite as like something in parentheses squared. Okay, so you have to remember to do that, otherwise you're going to get your constant wrong. Now once you do that, we are going to do a U-substitution, but it's going to be a pretty easy U-substitution. So we're just going to say let u equal 8t. So du is going to be 8 dt, or moving the 8 to the other side, dt is going to be du over 8. And then we take that and we substitute it in. So we substitute that into our integral. we are going to have negative 5 over 8 integral 1 over t square root. 8t squared is u squared, right? We've got our 8t squared is u squared minus 81. We don't care about the 81. The 81's fine. And then our dt is du divided by 8. Okay. So that's what we wanted. Now, why did we want it that way? Well, just with slightly more work here, I can write this as negative 5 over, looks like 64. If I just combine those 8s, right? Which 8s? That 8 and that 8. You can rewrite it now again, where I've got t square root. You don't really have to do this, but u squared minus 9 squared. As long as you can tell that that was a 9, which you can back here when it's an 81, then that's fine. So this is a equals 9, not a equals 81, not a equals 81. It's a squared equals 81. All right, so let's try to make this smaller so we can see. So compare that to what you've got in your problem up here, right? So we've got a t, they've got an x, that's fine. We've got a u. Whoa, 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 whoa. Did I not substitute in that t? Oh man, we gotta back this up. No, we don't. We can fix it. Okay, hold on. I'm gonna fix this. Hold on. Okay, let's keep going with the substitution because I just didn't do it. Right. So if you didn't catch what was wrong here, I have a du, I have a u, I have a t. Why a t? Just because I just forgot to substitute it. So we gotta substitute in for that t. So what's t? What's t? So you have to come back to your substitution here. Ooh, there it is. U over 8 is t, right? Just move the 8 over there. So let's make that substitution. So sorry about that. We have an integral of negative 5 over 64, 1 over t, which is u over 8, square root u squared minus 9 squared du. Dividing by a fraction like this is multiplying by the reciprocal. So basically that 8 is actually in the numerator. So it's going to go in the numerator. And we're going to end up with negative 5 over 64, but then times 8. Integral 1 over, can I write this here? U square root u squared minus 9 squared du. It fit. It's fine. So now you can cancel the 8 with one of those. We have negative 5 over 8 again. Integral 1 over u square root u squared minus 9 squared du, which now it matches the formula exactly, right? We still know the a. The a is 9. So it's 1 over 9 secant inverse x over 9 plus c. So it's 1 over 9 secant inverse x over 9 plus c. Not a lot you can do here. You can combine your constants. So 8 times 9 is 72. And that is about it. Come on, up, move. Okay. Small. All right, and that's about all you can do. Now that was a more elaborate U-substitution than I intended for it to be, but that's how you do these problems. Okay, so most of them are easier than this. I picked this one because it looked hard to me. So we did it, got it right. There we go. No, I'm still having trouble. What am I doing? Brain not working today, huh? So yeah, let's go back here. And what was U actually? I wrote X. I just wrote X, but it wasn't, was it? It was 8t. And 8t. Having done this, looking at the book's answer here, it looks like they're doing something strange compared to previous books that I've used. So what they're doing is they're putting this in absolute value. Okay? Which means that they must be using this as a formula. And whether or not you have to do that is really down to how they've defined these integrals. So I'm just noticing that they have it there. So they have it, so we should have it. All right. So let's do another one. Maybe find an easier one here. All right. Yeah, let's do a definite integral. So we got negative square root 3 over 2, positive square root 3 over 2, negative 9 over square root 25 minus 25x squared dx. All right. So I've noticed that the book really likes these. I keep saying the book, but you know, the online homework system. There's a 25 here and a 25 here, and these match. Right? Those match. Since they match, we do not need a U-substitution, okay? No U-sub needed if those numbers match. Okay? You can do a U-sub, but in my opinion, it's just, you know, it's just not worth it. So here's how I would do it without a U-sub. I would simply, I took the negative 9 out. So 1 over, what I would do is I would just factor out a 25 in the denominator, like so. So that's all I did was factor out a 25. But then that can be rewritten as negative square root 3 over 2 to positive square root 3 over 2. You can split that up now and take the square root of 25 out in its own square root. Of course, this is just a 5 in the denominator. So square root of 25 is 5, so you take it out. You have negative 9 over 5 integral from negative square root 3 over 2 to positive square root 3 over 2 of just simply 1 over 1 minus square root x squared. I said square root x squared, but square root 1 minus x squared. All right, so you end up there, and that did not require a U-substitution. Okay, so then you're going to look at this integral here and just say, well, what is this? And you know, if you compare it to the integrals we learned, it is a sine inverse. Specifically, it's not just a sine inverse. You can do this one, but it's even the simpler one, right? It's even the one that I said, do I have it? Yeah, it's even the simpler version of it, right? Because everything's a 1. So come down here and just say, well, that's going to be a sine inverse. So we're going to have negative 9/5. This is a definite integral, right? Limits of integration. So we got brackets here, sine inverse x, right? No U-sub to worry about. Negative square root 3 over 2 to positive square root 3 over 2. And then we're just going to substitute those in, right, for the fundamental theorem of calculus. So 9/5, parentheses, sine inverse square root 3 over 2 minus sine inverse negative square root 3 over 2, like so. At this point, you need to be able to figure that out, right? What's the sine inverse of square root 3 over 2? Now, you can use Wolfram alpha. That'll be fine. If you don't want to use Wolfram alpha, right, you can definitely do it by hand if you have like a unit circle or something. So, actually, do I have a unit circle? Yeah, there's a unit circle, right? So the sine inverse is only defined from negative pi over 2 to positive pi over 2, so that's on the right. So hopefully you can see that at pi over 3, you can't see my pointer, but right there, huge, right? So sine inverse of square root 3 over 2 is pi over 3, and must be down here. Sine inverse of negative root 3 over 2 says it's 5 pi over 3, but we should not call it that. We should call it negative pi over 3. So they're positive pi over 3 and then negative pi over 3. So let's go back. That should be pi over 3 and then minus pi over 3. So what do we get? That's going to be negative 9 over 5, 2 pi divided by 3, or looks like maybe I can do some canceling there with those. So 9 over 3 is 3. So I have negative 6 pi over 5, maybe? Let me just type that in here. I just want to double check that. What? Oh, no, I'm right. I just wrote down the problem wrong. I wrote, when I wrote it down, the top limit was supposed to be square root 2 over 2, but that's not the one we solved. So that's fine. So this should be right. Should be right. Okay. So those are basically the two type of problems that you have. You either have a definite integral that does not require a u-sub, or you've got a longer integral that does require a u-sub, but it's not a definite integral. Okay, and yeah, I'm gonna have another lecture today, so this is only one out of the two that you're gonna get, and I might start out by doing one of these more by practice if I feel like this was too short. Anyway, that's it for now.